opportunity to present ANTONIE today. ANTONIE is based on primarily a microscope that's an atomic force microscope. It was named in honor of the father of microbiology, Antony van Leeuwenhoek. The clever naming for that is due to Brent Christner's midnight acronym searching algorithm. I'm going to just get started here. I'll try this one. Okay, so as you know, one of the primary goals of the Europa Lander science definition team was to address characterizing biosignatures in Europa's near subsurface materials. There are a couple of objectives that we address with a microscope. The first is to identify and characterize morphological and or textural features in Europa's near subsurface. And the investigation that ANTONIE accomplishes here is to characterize particulates in the samples that are 0.2 microns to 1,500 microns in scale. The second objective that ANTONIE addresses is to assess the structural and compositional nature of Europa's near subsurface materials. There are two investigations here. One of them is to measure the mechanical properties of the sample, and the second is to potentially determine the composition of particulates. AFM, you may be familiar with. It's been around for about 40 years. Is a pretty simple instrument, and it works by a cantilever interacting with a sample. It rasters over the sample, and it creates a three-dimensional topographic map. AFM is often used in materials science and the semiconductor industry, but can also be used to detect biology. Particulates such as this cell were imaged in a 1999 paper. This came from Lake Vostok accretion ice. You can get really high resolution image at the sort of subcell level, even looking at textures that are on the cell surface. But in addition to getting a 3D topographical map, you can also get nanomechanical properties, things such as the sample stiffness, the dissipation of energy when the cantilever interacts with the surface, and adhesive properties. And so you can see how sort of a diagram of the cartoon on the top figure here. On the bottom is a scale showing the stiffness is measured as kilopascals over 8 orders of magnitude different between cells and hard materials like steel. So AFM biosignature detection technology, as we have thought about it, builds on spaceflight heritage. There are a number of assets to using AFM in space, in addition to its submicron 3D resolution and the potential for nanomechanical property determinations. These instruments are lightweight, they have a small footprint, and low power consumption. They can operate in air, liquid, and in vacuum. They've also been flown recently in space on 2 different missions. One of them was flown on the Phoenix mission, and the other on the Rosetta mission. In both cases, they imaged particulates on Mars, on the Phoenix mission, and particulate size distribution in soils. On the in the Rosetta mission, they measured cometary dust and observed large particle aggregates. Mark Bentley wrote a paper post the Rosetta mission that was really on lessons learned from operating AFMs in space, which we have adopted into the design going forward and thinking about ANTONIE. Some of these are co-registering if you use co-registering an optical microscope image with the atomic force microscope image, including an array of cantilevers that have different spring constants and different tip morphologies, and then being able to operate the instrument both in open and closed loop formats, which was required on the Rosetta mission. So one of the things that I think AFM has a real advantage to is detecting really small biosignatures. We don't know what to expect in going to the surface of Europa, and we didn't know what to expect when we went to Lake Vida, which is a lake in East Antarctica, and the lake in the McMurdo Dry Valleys, where the sample, and I don't know that you can see very well from the back, but you can see the really bright images here. These are what I would call kind of normal-sized bacterial cells. And this background, the sort of starry night, barely shows up when you're looking at really what we have is like one of the brightest DNA stains under epifluorescent microscope. If we look using an AFM, you can see really what these particles look like. You can zoom in at higher resolution and start looking at the surface textures of the cells. So we have also been interested in asking the question, can we discern biosignatures from abiotic particles using AFM based on their nanomechanical properties? This is an image that we collected where we mixed silica beads. So if I go back, let's see here. So the round features, which you may or may not be able to see, are silica beads that we mixed with bacterial cells. And if we look at the force curves from these particles, we can see that this is on a glass slide. So the black dots are plotted here on the graph. The glass background is not different from the glass beads that are in blue, and we have particulate organic matter that is, as Roger calls, the schmutz from the cells, that is in green. This is softer, and then even softer yet are the cells that are in the figure. We did a second kind of similar experiment, but in this case, due to a conversation we were inspired that we had with Mitch Schulte a few months ago, he asked us the question, could you actually discern the difference between carbonaceous chondrite meteorite and cells? And so we obtained some Allende crushed powdered meteorite sample. We screened it through a 5-micron sieve and mixed it with 3 different bacterial cell types. In this case, the meteorite, which is here in the particle in the middle of this aggregate of cells, shows up to be quite stiffer, not as stiff as the background of glass. And then the cells have different, they're softer yet, and they have different curves for the different types of cells that we had. In this case, we mixed an Antarctic bacterium called Pseudovibrio with Bacillus endospores and E. coli. So we think we can discern particles of different types of properties from life. You could imagine then that if we went and got a library of different types of cells and particles, that we might be able to just separate these in 3 dimensions, or in here in 2 dimensions on a graph based on their biophysical properties. As Peter talked about a little bit in his talk, but identifying morphological features of particulates in icy, potentially salty samples is going to require sample processing. And along these lines, we partnered with the Monterey Bay Aquarium Research Institute to develop a concept for this instrument, which would be a sample handling system. MBARI has a lot of history and experience in operating remote autonomous platforms in the ocean on Earth. This is the 2G ESP that was originally funded by a NASA A-STEP project with the concept that they would evolve this design into space-based operations. And the 2G ESP here is very large, but this is actually a functional molecular biology platform where it's not only processing, collecting samples and analyzing them, but also doing real molecular biology, DNA extractions, PCR, and remotely communicating that information back to the lab. They use titanium pucks, which are inert, for sample processing, and this system is again complete and remotely operated. They have a new system that they have integrated into this submersible, which is based on microfluidic cartridges, which it rotates around and is actuator driven inside the head of the submersible. So we have adopted elements from both of these designs into the concept for ANTONIE, in which the titanium puck would be delivered to the instrument. The central processing unit here then would accept the sample and take it, pressurize the sample in order to be able to melt it without adding heat, or very much heat, and then it would be passed through different screen sizes, and then those samples can then be rotated and passed by an optical microscope, an AFM, and potentially a third instrument that is on the lander. The design fits in the 10 centimeter by 10 centimeter space that was described in the PIP. So there's several elements that, even though we're basing this on the heritage design of what has flown before, there are a couple of upgrades that we can do 20 years later than when these developments were made. So piezo-resistive probes can be upgraded, as well as the actuator and fine XY scan range to move the sample. We think calibration targets are needed for every sample processed so that you can get tip shape on each sample, as well as the XYZ and mechanical force scales. Autonomous operations are going to require image analysis. Some of this can be adopted from heritage algorithms that were developed from the Phoenix mission, but we also have ideas for how to compress the data to preserve the high information aspects of it, as well as for developing neural networks for particle classification. This is based on work that was done at Oak Ridge and published several years ago with a project collaborator, Stephen Jesse. We also have, there's preliminary work that has been done with where you can use the AFM to do correlative mass spectrometry with particles. By heating up the tip of the AFM, you can volatilize a sample and bring it into a mass spectrometer. And so this could potentially really give us a lot of information about particles being observed. The advantages of ANTONIE then are that this has system, as we've designed it, has flexible architecture. We can partner with other instruments. Its integrated sample preparation system affords us to have high resolution image and property determinations. The topographic maps will be useful information regardless of whether the particles are biogenic or abiotic in nature. And the nanomechanical forces can potentially help us inform between life forms and those that are not life in terms of stiffness, adhesion, dissipation of energy. And even in the absence of life, I think that this kind of a platform can yield invaluable information about microscope materials and features in the near subsurface of Europa. The team here is large and great, and I have learned a ton from working with all of them. Roger Proksch is sort of the mastermind behind the AFM design. Chris Scholin is the chief and president of MBARI, and with Jim Birch and Doug Puckett have designed the Europa generation ESP. Thank you.
Yeah, given that you're looking at very tiny scales with AFM, how do you deal with searching for things that are extremely low concentration, that you're likely to see 100 per milliliter or something like that, so you have to search through a big haystack for?
So we have the concept is that we would concentrate the sample onto a pretty small surface, but also that we would first inspect the sample with an optical microscope and have a larger scale, and then be able to identify the high entropy areas of that image, and then localize the AFM to where to go do the work. And you can even still do nested scans like they've done on both of the other missions with AFM, so you can start larger and then go in a higher resolution at a smaller area.
Another way of distinguishing between whether you're looking at inorganic material or organic or biomaterial would be to do a tip-enhanced spectroscopy, such as tip-enhanced Raman or tip-enhanced infrared. And I know it's probably at a lower TRL, but what do you think about the possibilities of eventually moving to such an enhancement of the technology?
Yeah, I think that's a super interesting an area to develop for the future, and to get that kind of instrumentation into the sort of TRL level maturation, I think would be really awesome.
Yeah.